Topic is Diego Tonelli from INFN. He's an experimentalist that does flavor physics and has been working in several of the most relevant flavor experiments, CDF, LHCD, and now he's in Bell too. So he will be telling us about statistics. And I forgot to tell you before, but you are here because, not because you know everything, but because you want to learn everything. So you have to ask questions, okay? And it worked quite well for Andy. Please keep on asking questions. There is no silly question, okay? So, thank
yes,
you.
thanks. Hi, good morning. So I'm going to try to give you a very concise overview of what I think are the most relevant things in the business of statistics, especially focused on data analysis and on statistical learning or machine learning, you want to call it. Of course, your background in these things will be very varied and diverse, so I will necessarily make some of you happy at some times and unhappy at some other times, but hopefully in the end, I hope that each of you will get something useful out of it. So, this is who am I? I'm not going to present this, but I just want to underline that I'm very happy to talk with you at any moment in the school, during the lecture, after the lecture, and even after I leave. I'm going to leave on Wednesday, but you can reach me in my mail here if you have any questions or doubts or something related to your work that you think I can give you some comment on. So statistics. There are many definitions. This is one possible definition. So it's just the science of learning from the data by identifying the properties of the population of natural phenomena and trying to quantify the information that we get from it and the uncertainty on that information. So statistics allow to design better experiments, to communicate better our results, and to ultimately get a better grasp on the physics. And it is going to, divided in many different topics, but what is most relevant for us is basically modeling, point estimation, which means measurement with a central value and uncertainty, in interval estimation, hypothesis testing, and goodness of fit. So first of all, why do I need statistics to do physics? Not all scientists use statistics. For instance, if you are an entomologist and you find a funny new insect, you do not frequently to do a lot of statistical analysis to understand that you are looking at a new animal, a new insect that nobody has ever classified before. Similarly, if you see a flying donkey, you probably will scratch your eyes, you try to wake up, but if you are sure that you see it, you don't need a statistical analysis to figure out that you're seeing something new and unexpected. So why do we need statistics instead? We need statistics because what we see is rather stuff like that, where there is not an obvious striking content of information that tells you that you're looking at something really new. It's very rare in our field, it happens sometimes, but it's very rare in our field that you really see on an event-by-event basis something strikingly new, okay? And so you have something like this and you want to know if something like this is basically standard donkeys or if there is a flying donkey hiding in your data, okay? And so these are some of the questions that we usually ask ourselves when looking at the data. Are our data just explainable with background only, or there is evidence of some anomaly going on? And whether there is an anomaly, is this anomaly maybe an artifact of our instrument, or is really new physics, new dynamics, and stuff like that? So basically, statistics helps us in understanding nature from blurred observations. And this is particularly important now, these days, because the progress in physics is sometimes have gone through various phases. There are phases in which the progress is more top-down, so to say. So you have a very firm and solid theory that makes very precise predictions. And then when you are in this situation, You only need a very little data carefully chosen in the right region of the dynamics to make progress, okay? And this was, for instance, the thing that we had with the standard model up to recently. So from the end of the 70s up to a few years ago, we had a very solid theory that tells us where to go and look for new phenomena or for completing the theory. So this was the top-down thing. And there, it's really the theory who drives the progress, who tells you where to look in the data. But then, when you don't have this scenario, the situation is much more leaning in favor of the data. The bottom-up approach is, in fact, when you really have no strong theoretical guidance, and you really need to get from the data the direction. You need the data to inform you where to go. So, in fact, from 1967 to 2012, we had this top-down comfort, which driven a lot of progress. And now we are in the other situation, right? Now we are probably entering a novel data-driven era, which will help us answering some of these important open questions. You will recognize some of the most famous here, but you can put whatever you like. You know, is mass hierarchy of neutrino normal or inverted? Is neutrino a Majorana thing or a Dirac thing? Why do we have three families? Why they have the hierarchy of masses, etc. So it looks now a particularly suited and fitting time to learn how to best use data, because probably your career, especially with the experimentalist among you, will be focused a lot on that. So today I'm going to give you a quick recap of the basics, very quick, but it's important to at least define some notation and names. And then I will talk quickly about probability, and then I will spend more time on inference, and I'm going to try to go until the interval estimation, in particular the Feldman-Cousins likelihood ratio order. And then tomorrow I will discuss a little bit about the role of the model and nuisance parameters, so-called systematic uncertainties, and then go to hypothesis testing and introduction to statistical learning. So I have to cut a lot of material, so apologies if your favorite topic is not there, or if you already know everything of this, please feel free to come to me offline and we can discuss whatever you like. I hope to be helpful. So, quick recap of the basics. So the fundamental notions that subtend these statistics and the inference is the fact that we are dealing with random events. Okay? So random events are events that allow for more than one possible outcome. Okay? So before the event happens, you do not know what the outcome will be, but hopefully you know the probability for each of the possibilities of that. Okay? And then if you associate to each random event some variables, some variates, some things you can measure, then, which are called variates by the statistician, but are what we call random variables or observable, then each of these observable will have a frequency distribution, right? Which depends on the distribution of the outcomes of the random event. And then if you normalize this frequency distribution, you have a loosely defined probability distribution. Okay? So the idea here is that a collection of random events forms a population. Okay? And a population is the hypothetical infinite set of repeated experiments, nearly identical experiments, of which we want to measure some feature. Okay? So the goal of the first part of this course, which is focused on inference, is how do you quantify the collective properties of the parent distribution, of the distribution of the population, if you only can access one single sample, the one that you observe. Okay? Please ask questions if something is not clear here. Okay? So the parent distribution somehow is some idealized concept here with infinite statistics, of course it's not possible, from which everyone who does an experiment on this particular process will observe a sampling. So this is experiment 1, experiment 2, experiment 3, blah, blah, blah. So these data are all different among them, but they are drawn from the same parent distribution. And so we try to measure this, observe this, to get the properties of this. Okay? So this might look a little bit abstract, but in fact is what you do every day, right? I mean, if any of you have ever made an histogram, or a counting experiment for that matter, you will probably have seen that the data points that you observe, here it's an X mass from atoms, but it's irrelevant. The data points that you observe have error bars, okay? So what these error bars are? Anyone?
A range within you are confident in some amount of that the value you've plotted is actually right. So it's some allowed range within a certain amount of confidence.
Yeah, you're approaching that. Yeah, thanks. So these bars are not an uncertainty on your observation, right?
But on statistic.
Sorry?
But on statistic.
These are take them as statistical only. Don't worry about systematic for the moment. But if you look at the events that are in this bin here, 105, are we uncertain that we observed 4 events? No, I mean, physics is difficult, but counting events cannot be such difficult, right? So we observed 4 events. That's sure, period. These are 4 events. So why do we put the bar here? The bar represents the fluctuation in the counts of that bin that one would expect if the experiment would be repeated. So if you repeat this experiment and do the same histogram, you would expect your observation in this bin to fluctuate in this range with some probability. Okay? So that's exactly what I meant before. This is the sample you observe, but you're trying to infer what would happen in other samples. You're trying to observe what happens in the parent distribution. So you probably are all very familiar with what the probability density function is. But this is just one slide recap. So if you look at the frequency distribution of our observables, you observe that many of them are quite regular, quite smooth and nice, okay? And so you can make an idealization of this distribution and you get to the probability density function. So if you have an observable, X, these are the data. In all my talk, all X are the data, okay? If you have an observable X, the probability density function of X expresses the elementary frequency that you see for each value of X in its range, okay? So, and if you put the range to 0, the probability that X is contained in this elementary range is Fx times delta X. Okay? That's easy, you know it certainly. What you need to keep in mind is that the probability density function, first of all, is a function of the data. That's quite obvious. This is not a probability. It's a probability density. In fact, the probabilities have no units, but this has units of x to the minus 1. Okay? And for the discrete variable, this is called probability mass function, but it's the same thing. Don't get confused by the names. And another important thing of this function is its integral from minus infinity to some point, x, which is called the cumulative density function. We'll see in a second why this is important. Okay?
Can I ask, are you making a distinction between the different outcomes that are available and the different measurements that you can make?
In here, you mean?
Yes, so when you say that the probability density function is a function of the data, this is obviously a function of which observable you pick. So is there some subtlety?
No subtlety. Okay. It's just that you pick an observable, you pick a process, and this f of x expresses the probability or the normalized frequency that this process yields each of the possible outcomes. Okay? The subtleties will come later. So you probably also are familiar with that, but this is just a quick recap. If you look at PDFs, probability density function in more than one dimension, which is the usual case in our work, there are a couple of jargon things that you better learn, which is the fact that the full-fledged two-dimensional PDF of two observables as a function of some parameter m is called the joint PDF. Okay, the joint PDF is this guy here, and it encapsulates all the important information about the probabilities for these processes. Then you can define out of this two-dimensional space two one-dimensional things, two n-1 dimensional things, which is one is the conditional PDF, which is written like this. Unfortunately, also the writing has some relevance, so please try to remember it. F of x2 given x1 of a parameter m. This is the conditional PDF. So this is related to the probability that x1 is in a certain range given that x2 has a specified defined value. This is inverted. I made a mistake. So probability of x2 to be in a range given that x1 has some value. Okay? I'll correct the slide before putting that. So this is this thing here. So you basically plot x2, okay, in a slice of x1. Okay? This is a conditional probability. And then you can also somehow integrate, project this two-dimensional function along one of its dimension and get the marginal PDF. So the integral of this in dx2 is the marginal PDF, so it's related to the probability that x1 is in a certain range regardless of the value of x2. We don't look at x2, we don't care, we just want to know what x1 is. Okay? And this of course can be generalized to multiple dimensions. There are various ways of characterizing, describing, if you want, the PDF with which you're probably familiar, so I'm not going to spend much time on that. The PDF imposes a weight on each point of the sample space, on each x, right? And so it can be used to obtain an average value of any function, g of x, of the random variable. So this is expressed like that. And in analogy with what you do with your sample distribution, you can define an expectation value for your data, which is this integral here. You're certainly very familiar with this already. Or an expectation value for the quadratic deviation of your data, which is the variance here. Okay? Are you all familiar with this? Very good. In some cases, it is handy to remember how do you, if you have a PDF of a variable x, how do you get the PDF of a function of that variable x? So x is a random variable, right? And it has its own PDF. A function y of x is also a random variable. Is also something that has possible outcomes. And you want to know how it is distributed. So the way to do that is to impose the conservation of the probability in the two matrices, the x matrix and the y matrix. Because the probability should be conserved, cannot be depending on the matrix you look at your problem, right? And then if you do the algebra, which I don't spend time on it, because also this is probably known by many of you, you get the expression that relates the PDF of a random variable x with the PDF of a function of that variable, okay? And you see immediately that there is a Jacobian here, which takes into account for the expansion of the matrix or contraction of the matrix, okay? This seems technical, and it is, but it has also some conceptual nice consequence. And this is the way I put it here. And this is because I want you to learn from the very beginning that any inference that is based on the maximum of the probability is ill-defined, because the maximum of the probability depends on the matrix. Okay? So if you do a measurement in X and have the probability of getting X, and then you do an inference on your parameter based on that, on the maximum of that, you will get a different result from your colleague that instead of X is looking at X to the cube, for instance, and makes another inference. So keep in mind, using the maximum of the probability as a good figure of merit for an inference, we'll see what an inference is later, is not a good idea, because it's arbitrary, it depends on the metric. Okay? And another important thing related with that is the special case in which the function y of the random variable I choose is actually the cumulative. You remember the cumulative we just saw? If you take as a function of your random variable its cumulative, you get a very nice result, which tells you that the PDF of this cumulative is constant, is uniform. What does it mean? It means that any continuous distribution can be transformed into a uniform distribution. Okay? And you say, and so what? The reason why I tell you is because there are, in many inferences, especially Bayesian inferences, people tend to give to the uniform distribution a particular conceptual value. They say the uniform distribution is uninformative, blah, blah, blah. This probability integral transform, this relationship here tells you that the uniform distribution is no different from all the other. It's just a metric transformation from any other continuous distribution. So it has no special role. Okay? This now sounds a little bit up in the air, but you will see when we get there. All clear so far? Don't be shy. Tell me. All right. Thank you for good.
Yeah, I have a question.
Yes.
You said that using for the estimator whatever maximizes your PDF is not a good idea, right?
No.
As an estimator, whatever maximizes your PDF is not a good idea.
No. Wait a second. I say that we will see later that estimates based on the maximum of the probability are not a good idea because they depend on the metric of your chosen observable. If you choose X, you get an estimate. If your colleague chooses sine of X, he gets another one. Or logarithm of X, you get another one. Okay? So it's usually good, you will see later, it's usually good to, when you do inference, to do things that are not arbitrarily dependent on the metric. Because it sounds wrong, right, somehow.
My question is, what about the maximum likelihood estimators?
The maximum likelihood estimator, which we'll get later on, is a different thing, because there you look at the maximum of the likelihood, not the maximum of the PDF. There are two different things, and it's very important to keep in mind the difference. I will insist on that later. Okay? So let's go to the more interesting stuff. This is our description. Let's go to estimation. So the thing is, can we make objective and informative statements about a population when only a small sample is available? Except trivial cases, one cannot do it just using deductive logic, okay? We need to somehow associate some concept of probability to quantitative findings and propositions, because we are not observing the whole parent distribution, we are just observing a single sample, okay? And here, when you go and talk about probability, unfortunately, the statisticians divide in two schools, because the definition of probability differ, and so the inference and the techniques associated differ. And today, I'm going to give you I hope, ecumenic view with pros and cons of each, and then you will decide what is more suited to your way of thinking. So the theory of probability is a branch of pure mathematics based on axioms, blah, blah, on axioms, etc., based on set theory, measure theory, and event integration. The theory of statistics, in fact, instead, is essentially inductive and empirical. It's not as rigorous and nice as the theory of probability, because it attempts at inferring the values of unknown parameter from observation of events. So a typical probability problem is try to find the probability of observing j heads when tossing a coin n times, if you know that the probability of that coin is something. Okay, that's a probability problem. This is as a mathematical solution that is exact, there's no questions about it. A statistics problem is the inverse one. I toss a coin n times and get j heads. What's the probability for that coin? So it's the other way around, see? And it's not as rigorous and nice as the previous one. The fundamental ingredients to do inference are three, right? You obviously need the data, x, okay? You obviously need some parameters you want to estimate, m. I'll try to keep the notation consistent throughout the talk. And the most important thing, you have to assume a model that connects the two. A model that once you observe this, you can infer this. Otherwise, there is no inference. All right? The model is a very important piece. And it's a mathematical structure of the form probability of data given the physics, in our case. Okay? It incorporates all the physics, knowledge, intuition, and best describes the relevant relations that we know between the observables that we measure and the parameter we want to estimate. Okay? It's important to understand that this is a probability model. Okay? So you do not know exactly what value of x you would observe, even if you were to know exactly the value of the unknown parameter. So even if, I don't know, nature, God, whoever you want, come and tell you, look, the mass of the gravitino or whatever is this, you cannot rigorously predict the outcome of your experiment. The outcome of your experiment will be a distribution of possible results. Okay? And the width of the distribution, the width of your model, is actually the uncertainty that is associated with your inference.
What is meant exactly by the width of the probability? Is it the width of this width of P?
This is the variance, basically the variance of your estimator. You will get there. Is the width.
The inference.
Yes, the estimator is something used to do the inference, and it has a distribution. How much broad or narrow it is, it determines the uncertainty of your inference. How good you're approaching the unknown value of
But
m.
at this moment, I mean, you are just, I mean, this is just a probability, right? So given m,
Yes.
what is the probability to get x,
Yes.
right? So you haven't done anything inference.
No. But this will, the model is then used to do the
Yeah,
inference.
yeah, but you haven't yet.
Yeah. No, I haven't yet gotten there. So it's important to understand that the model is the fundamental building block of most inference, both in the frequentist and the Bayesian schools. This is the step everyone agrees on. Okay? Without the model, it's very hard to make an inference. And so the model gives the probability to observe data assuming physics. And so this is the forward process, from the physics to the data. The forward process, of course, for instance, in experiments, you don't know the physics, but it's there, and you see and you produce the data. Or also in simulation, you know the physics, but it's not necessarily true, and you produce the data associated with that physics. Okay? The backward process from the data to the physics is what we call inference. Okay? So, the probability in terms of mathematical definition has been defined by this guy here, and you probably are familiar with it. I'm not going to spend time, and it's basically defining a sample space omega with all the possible mutually exclusive outcomes, and then assume that the probability P is an additive function on the set and is immeasurable continuously from 0 to 1. And then if you define that is non-negative for each possible outcome, and the sum over all possible outcome is unity, and the probability for observing independent events is this, then you get a mathematically rigorous and consistent definition of probability. Okay? Unfortunately, this definition is too broad, is too general to allow for application in inference. And so various people in the last 200 years, 300 years, have come with definitions that are more operative, that they can be applied to do the inference, okay? And there are various heuristic definitions, which I put it here, and I'm not going to discuss it, you take it for reference. What I want to discuss instead is this basic pair of definitions. So there are two definitions that then determine the inference school that we have. One is frequentist probability, which is defined as the limit for the number of trials that go to infinite of the fraction of successes. Okay? So you have a process, you try it many, many times, you define your success as the happening of event A, and so the fraction of successes over the total of the trial is, you bring it to the limit, this is the frequentist probability. Okay? So this is, already from the definition, this requires reproducibility, repetition of the experiment. Okay? If you cannot repeat the event, you don't have a probability associated with it. And in this definition, data are random, but theories are not, because you cannot repeat a theory conceptually, right? You cannot say, okay, let's draw a distribution of Higgs boson mass. Nature has one Higgs boson mass, we don't know it, we try to infer it, and so this, you cannot associate a probability to a constant of nature, for instance. Or you cannot associate a probability to something that is not repeatable, as if it will be raining in 20 minutes from now. There will be only one single time in history when it's 3 of June at 11:50, and it either rains or not, but you cannot repeat it. It's only one, okay? So you cannot associate a frequentist probability to that. And another thing you learn from here is that the frequentist probability definition uses information that comes from the observed data and from all the data that could have been observed but have not, because you somehow allow for repetition of your experiment. Even if you don't do it, you can simulate it, for instance. So this is one definition. And this definition restricts deduction to what you can get from P of the data given the theory. Okay? You do not associate a probability to the theory, so you don't have P of the theory given the data. Instead, this is what you get with the Bayesian definition of probability. So this is the subjective degree of belief on something happening. It's really subjective, so it's really something that you use all the knowledge you have, all your intuition, all your thinking, and assign a probability to some event. Will be raining in 20 minutes, I don't know, maybe 20% probability. Will the graviton exist? I don't know, I think so. This is the kind of reason which is much more close to our own everyday reasoning. The thing that some see as a problem is the fact that same data and different scientists could have different probabilities associated with the same event. So could get different inferences. And this might create some problem in terms of reproducibility of the result. And the fact that we want the result to depend mainly on the data, not on the personal opinion or belief of an experimenter. But the Bayesian probability gets you to know what's the probability of the theory given the data, which is the really important thing. You observe the data and you directly have some information about the theory. So that's the really interesting question you ask yourself. This is not available here, okay? So here the scope is broader, it's applicable to more problems, but you need to be accepting that there might be some subjective information associated with it. Here the scope is smaller, okay? So this is a funny thing that I'm not going to spend time about. One important thing about probability in either definition is to be sure to define very well the sample space. The sample space is the sample of all possible outcomes. Why is that important? Is that important because it changes, this is the denominator over which your frequentist probability, for instance, is defined. And so if you change the denominator, it changes the probability. So it's important to define it very well and very, very precisely. There are very famous paradoxes in literature about the poor definition of the whole space. And they are used also in for instance, in marketing. For instance, perhaps have you seen that some airlines market their flights, and 90% of our flights arrive on time. Okay, I say, oh wow, I'm going to take this airline. But then they don't tell you that flight that delay for more than 3 hours are cancelled. And they don't enter the denominator, right? So this is, this is somehow cheating, but this is a poor definition of the sample space. Or our survey shows that most people lose 5 kilograms in a month on this diet. This is just because the people who have done the diet and lost weight, they were enthusiastic and they sent back a feedback email, say, oh, I'm happy, your thing works. And the people who tried the diet, they didn't lose weight, they just say, oh, fuck it, and and they never answer. Okay? So let's go to Bayesian inference, which is closer to our thinking, and it's also easier. Bayesian inference rests on a very important relation between conditional probabilities. So, like I said before, P of A over P of A given B, if A and B are random events, random variable, is the probability of A given that B has occurred. Okay, so the probability of A happening under the condition that B has been happening also. So you are restricting the sample space to B. The new sample space is smaller because you have asked that B happens before checking what the probability for A. And if you follow the reasoning, then you will see that probability for A given B is the probability of the joint probability of A and B divided by the new sample space. So probability for A given B is probability of A and B divided by PDB. Right? But you can basically reverse this and say the probability of A and B is probability of A given B times probability of B. And analogously, you can do the same thing by swapping A and B. So the probability of the joint probability of A and B, the probability of B after asking that A has happened, times the probability of A, that A happens. Okay? So if you put together these two relationships and you equal them, you get this. Okay? So the joint for A and B is either the conditional of A given B times B, or the conditional of B given A times A. Alright? Are we clear on that? There will be also a picture later that shows that better. So Bayes uses this for getting his theorem here, which is exactly that. So the probability is a theorem that yields a key relation between the conditional and marginal probabilities, and it's written here. It's the one that I just told you. So the probability of B conditional to A is equal to A conditional to B times PDB normalized to PDA. So if A and B are all random variables, this is indisputable. This is true, it's very useful. For those of you who get confused like me on A and B's, this is a nice pictorial depiction of this. If you take the whole space, you take PDA, which is this, PD over the whole space, PDB is this over the whole space, and you do the small sets and you get this relationship here, which is in figures what I just told you, okay? It's sorry for the disgusting figure, but it's important that you remember a very important thing, that PDA given B is not equal to PDB given A. This is very important. These two things are different. Okay, they have different denominators, different everything. In fact, if you define variable A as pregnant or not pregnant, and variable B as male or female, then the probability of being pregnant, if you are a female, is 3% approximately on some population. But the probability of being a female if you're pregnant is much more than 3%. Okay? So please remember this. These two things are different. So of course, if you can use the Bayes theorem for making inference. So if X and M are random variables with non-probability distribution P of X given M, with X observable and M inobservable, you observe X, and what can I say about M? You do your Bayes relationship, and you get the probability of M given X. So the probability that M is true given that you observed X, which is exactly what you want to know. Okay? So if these two things are random variables, this is very nice and very powerful. Here I have an elementary example. I'm not sure I have the time to go through that, but I'll go quickly and then you can work it on a slide. So if you have 3 bags, each bag with 2 balls, okay, and you can have black balls, 1 black, 1 white, and white balls, okay. So you take a bag, you don't know whether it's bag A, B, or C, and you pick up a ball and you look at the color of the ball, okay, and then you want to infer from the color of the ball whether you have picked originally bag A, B, and C. Okay, this is an inference problem, very basic inference problem. Okay, you have two variables, 2 random variables. One is class of the bag, and the other is color of the ball, and you apply Bayes theorem straight there, and you get your result. You can work out later this. Okay, you have 3 bags, so you 1/3 for picking each. Probability of being white in the first bag is 1. In the second is is half, and the third is 0, and you work your Bayes theorem and you get your inference. Period. You're done. So this is to say that when all the elements of your problem are random variables, it will be stupid not to use Bayes theorem to do an inference, because this gives you the most of the information. Okay, it's a theorem, it's not an opinion, it's not a suggestion, it's a theorem that works, okay? So everybody used that. And it gives you all the information you might want to know. Because once you get out to the probability of M, the posterior probability, so this is here, sorry. You start from your model, but then using the Bayes theorem, you get the probability of M given X. And this is a distribution that tells you all the information you want to know. It's here, right? This is the unknown parameter you want to infer. This is his probability posterior distribution, and you can decide to take the maximum probability point or the average point, or take an interval that covers 95% of the values, etc. You can do whatever you like once you have P of M given X, the posterior density. Okay? And in many sciences, you do that all the time in medicine, in biology, because you know the priors. We'll get to what the priors are in a second. The problem is, the discussion starts in physics once the parameter you want to infer is not a random variable. For instance, is a constant of some kind of theory, or is an hypothesis. I mean, this particle exists or not. So when M is no longer a random variable, like which is my bag, okay, but it's a constant of nature, then here is where the two schools part. Because frequentists, they give up on getting the posterior probability, the probability of the theory given the data. They say, no, I cannot repeat the theory. The theory is one, has a fixed value for the parameter. I cannot associate a probability to that. I give up trying to get it from my data. Okay? Bayesian instead stick to Bayes' theorem by assuming the prior probability for that hypothesis or theory M. Okay? Because without, if you don't have P over M, P of M, you don't get the Bayes theorem to work. So frequently say, I don't know that, I cannot define it for a theory, for a hypothesis, I give up, I just stick with the likelihood. The Bayesians say, no, let me assume that. Let me take whatever I know about this to assume that and still use the Bayes theorem. Okay?
So I have a question.
Yes.
So in the simple case that you gave before of the balls, the colored balls in the bags, is
Yeah.
here the prior is that you have the different, the two white balls and the two black balls and the one white, one black?
Yes.
What exactly is, okay, that is.
Yeah, that's it, you see. Sorry, I could not discuss it. So here, the prior is this. This is the prior.
So
One third prior probability of picking bag A, one third prior probability of picking bag B, one third prior probability of picking bag C. Assuming that they are indistinguishable and you take them.
Okay.
Okay? Now the bags are a random variable, so there's no problem here.
Yeah.
Now if these guys are the masses of Bluino, then it's a different thing, right? Because some people like to think, in my opinion, the masses of Bluino can have this range of values. Some others like to think, no, if the Bluino exists, it has one value of mass with unit probability, no more. Okay? So, if priors are not known or cannot be defined, the frequentists make a step back and say, sorry, I surrender, I just use the likelihood. Bayesian assume the priors. And here, and one of the common strategies here is to take, since you typically don't know about the real prior of a parameter, you say, okay, I don't know anything about it, I take a uniform prior. A uniform prior is taken assuming that if it's flat and uniform, then I'm giving equal weight to all the possibilities. So I'm not cherry picking anything. I'm objective somehow. And this is plausible and has attractive practical features, but in fact, conceptually, it has some issues. And one of these issues, for instance, is that what is a prior in one parameter, a flat prior in one parameter, won't be flat into another parameter. Okay? Neutrino mass or square neutrino mass, whatever you like. Okay? Logarithm of something versus something.
You mean a function of
Yes.
any other function?
Yes. Any other, I mean, you typically you pick a theory parameter, but sometimes is arbitrary. Sometimes you can, some colleague of you take another function of that. And so if you take a prior that is uniform in one parameterization, it won't be uniform in another one. And the two inferences will give you different results. So now there you have one arbitrary choice, which form of the parameter I want to use in my inference, which give you two different results. So there is some people that are not comfortable with this kind of thing and prefer not to use Bayesian inference in this case. Okay? Is that clear? No.
So
Yes.
if I, for example, have one person says let's do parameter x, one person says let's do parameter x squared, and there's some prior, so person x squared is maybe preferring, I can't work out either the higher or the lower x's perhaps.
Yeah.
And then when I do my inference and they get their posteriors, the posteriors are going to be in the direction of truth, is that right? Are they going to, even if they started off by assuming the prior was basically assuming something very large, their posterior would be moving that down, then down lower towards...
It depends. It depends on your data.
Okay.
It depends on your data. So what the prior is very powerful for your inference. For instance, where the prior is 0, there is no data you can observe that will give you a
What do you mean prior is 0?
If you take a range for your parameter where the prior is 0, there is no observation of your data that will give you a posterior there, because the prior suppress everything. Right?
So you mean that the P of n is 0?
Yes, you take a range and you say, okay, here, I don't think the mass of the Arduino will be here. I put it in 0 here. It's, and then you observe all your data there. Your prior suppress all the values there, and your inference does not allow for a Arduino mass in the region where most of the data actually were. For instance, this is a paradoxical example, but it can happen in principle. Okay?
But I guess for masses you do all the time these kind of things, because you assume that a mass is negative.
No, not negative is one thing, but it might be 0 at very high values or something.
So if you said it cannot be negative, it's not a problem if you are...
Well, a physical, if you can write a Lagrangian with a negative mass, I'll be happy, but I never, never tried, never managed to. Of course, the model you takes into account the physics, so if it's a mass, it's positive. But then, it's positive means from 0 to infinite. Then maybe in your prior knowledge, you decide that some very high values are at 0, because they're unlikely in your opinion. But it's not, I don't want to focus on the mass, I just want to focus that the prior is not a small technical detail that allow you to do an inference. The prior is statistical information that you inject in your data, which is fine as soon as you say it, you document it, and especially, and we get there in a second, you check that your result does not critically depend on this information you inject. Yes?
So what if you have a scenario where you're doing like a simple resonance search and your experiment cannot probe very high masses? Like say like 100 TeV will never show up in your experiment.
Yeah.
In your experiment if you have 100 TeV mass. And you set your prior to be a flat prior that cuts off at the edge of where your experiment can probe.
But that's not a problem, because also the model is there, it's 0 there.
So, but you say you don't know, the model you're leading the mass is like this, you don't know what the mass is.
No, but the model of your measurement takes into account the sensitivity of your experiment. Mm-hmm. So if your experiment cannot probe masses that are higher than the collider energy, your model will have that.
Yeah, but the answer to your inference would not depend on the fact that you have decided a flat prior over only the range of your experiment versus the whole range.
No, in that case not. In that case not, because also your model is 0, so 0 times 0.
No, what I'm saying is that if you infer something for a resonance mass, and you assume a prior that is flat within the range that your experiment is sensitive to, and 0 otherwise, versus you assume a prior that is flat over a much larger scale that you are not sensitive to, the two results should give the same answer.
Yeah, they do, because in one case is the prior which is 0, and the other will be the model that is equal to 0, so probably. Okay? Go ahead.
Sorry, just one more question. Could you clarify point 2 there, please? When you say that uniform pairs put most of the data into?
Point 2 here?
The next paragraph. Yeah, so point 2.
Point 2. Yes, this is a geometrical property. If you have a multidimensional space and you take an hypervolume that is flat, you'll see that all the information goes at the corners. All the volume goes at the corners.
Is that the same statement as saying if you have a number line with a very large limit and you throw a dart, you expect it to be big, or is that different?
Wait a second.
Is it the same as saying if you have like a number line between 0 and a very large number and you just guess a random point, it's likely to be very big?
Yes.
Is that okay?
Is a geometrical. You can. Go ahead.
But that would depend on the choice of the flat prior, right? I mean, arbitrarily.
Yes, in your metric, if you make an hypercube that is flat in all the thing, you will see that when you project it, I mean, all the information is pushed at the corners. But these are more, I mean, these are points that are discussed, but the very, for us, empirically, the most relevant one is that the prior carries information. And that's why bias uses it. I mean, so when this information is there, it's good to use them. When you assume it, it's good to make sure that your inference does not critically depend on that information, I think, for a scientific result.
But if I have like a Gaussian likelihood and I have a uniform prior on some decent range of that, I mean, the posterior is going to tend toward the center of the...
Yeah, exactly. Yeah. So, of course, what Bayesian's inference do is, knowing that the prior injects information per problem, is to actually check the sensitivity of your inference against various choices of the prior. Because of course, if you can show by changing the prior that your result do not change too much, you're basically showing your colleagues that you are quoting an inference that is solidly based on the data you observe and not on the opinion of the analyzers. So this is really important, and in fact many serious Bayesians do that to show that
So is this a standard procedure?
Unfortunately not, but it should be, and I hope it will be, because it's
But
like,
I mean, the possibilities of trials of changing priors is
are infinite. Yes.
So what is there some, some...
Try logarithm. Try x and logarithm.
That's
If you
it.
get the same results, you're already in very good shape. Yes.
So I think this might answer my question, which is, like, do you have to do this in good faith? Because I can imagine if you want to like test the sensitivity of your inference based on the prior, you could do this in bad faith and take just a really terrible prior, and you get a big change on your inference. Does this mean that your result is bad, or that you just chose a prior that was deliberately bad?
Well,
and then what does it mean to vary?
So the moral honesty of each of us should never be at stake. I mean, I hope that people, when they quote the results, they're honest. Of course, if you swipe under the carpet the problematic prior and just show me the right ones, what can I say? I mean, we are human. Everyone is human. Typically, already trying, knowing that first of all, you say which prior you assume. That's already. Then try various ones, and of course, and then it's up to the reader of the paper makes its own judgment on whether you've been honest or not.
So at the end of the day, varying the priors doesn't like remove the subjectivity from the choice of the priors you use. You have to sort of
It doesn't remove the subjectivity, but I mean, the subjectivity is inherent to the Bayesian thing. So Bayes and his followers want the subjectivity to enter there. It's actually the philosophical point. So, of course, for physics result, we are a little bit uncomfortable when there is too much subjectivity in a result. And so people does this kind of thing to make sure that all the also the colleagues who are not very much comfortable with the Bayesian treatment see the result to say, okay, but this is really an inference that takes information from the data, not from the prior that was
Well,
injected.
in your example before, where everything was clear, random variables, and
Yeah.
you said, okay, I have a 1/3 probability of picking each of the bags.
Yeah.
But imagine that probability is not 1/3, it's not the same for all of them, and you still assume it somehow.
Yes.
You will get the wrong answer. Right?
Yes, but still,
This is a very obvious way, case where Bayes will fail if you don't have the right probability of
Yes.
M, right?
yes, yes. And as soon as they are bags, we don't care. But if it's physics parameters that go into the PDG, we may care. On the other side, I'm of the opinion that if you say what you do, then everyone will be
Under
free.
this assumption,
Yeah.
that's the result.
Yeah,
You
that's-
always have to say what you're assuming.
Yeah. So then, we are very, very slow. What can be computed without priors? So not P of the theory given the data, right? That is not accessible without the prior. So what we can do is to use the likelihood to favor or disfavor a certain theory based on how likely that theory is to give the data we observe. Okay, this is what frequentists do. And we get to the likelihood. I remember there you asked me some question about PDF and likelihood, so here is the slide. The likelihood function is the PDF of your data once the data are fixed, and the PDF is seen as a function of the parameter. Okay? So you have your model, P of x given m. If you fix the physics parameter and allow this to be a function of x, this is the PDF, what we talked so far, right? This is the PDF. If you instead fix the data you observed and let this be a function of m, of the theory, of the model, then you get the likelihood. Okay? This is what you maximize when you do an inference. So the likelihood is connected to the probability for observing the data x for different choices of the value of the parameter m. Okay? This is very important. Please have a look at that. This is the probability for observing a set of data for each possible value of the parameter m. This is not the probability that m has some value.
So then this means that if you're doing the Bayesian analysis, it doesn't make a lot of sense to quote whatever parameter maximizes your posterior, right?
So the likelihood and the posterior are two different things.
Yeah, that's why.
The likelihood is an ingredient that combined with the prior goes into the posterior.
Sure.
But here we're talking about the likelihood, and Bayesians have nothing to object to this. The maximum likelihood estimator is something that has very nice properties demonstrated mathematically, so there is no, no doubt about it. Okay? But what I'm insisting here is that the likelihood is not the probability that m has some value. The likelihood is the probability of observing some data given possible choices of the theory. Okay? And the likelihood is a complete summary of the data information. That's very nice. In principle, you can take an experiment run for 10 years, look at the data, construct your likelihood, and that likelihood contains all the information that is relevant for that inference. You could publish that. It's a very powerful reduction of information. And in fact, I hope that we will be converging in future, instead of publishing results, to publishing likelihoods that could be used in computer-readable form, and everybody can do his own inference. That would be a great thing.
But doesn't that depend on your choice of models?
Yes, the likelihood
So
is the
you
model.
have
Yes, the likelihood is the model. Yeah, of course. But also the result that you now quote it as the model in, but you cannot somehow, you have a very reduced amount of information associated with it. While the likelihood is a complete summary of the data. Okay? It's your model, and it's the single stronger driver of performance. If you want to improve your measurement, improve the model. Don't care about machine learning, improve the model. That's the way where you get order of magnitude improvement. All the rest are details. Okay? So the likelihood is not a PDF. The PDF is function of the data x. The likelihood is function of parameter n. And in fact, the PDF is normalized to 1 because it's a probability. The integral is a probability. The likelihood obeys no particular normalization. We don't care the normalization of the likelihood. And the likelihood maximum is invariant under reparameterization of m. So what maximizes the maximum likelihood estimator of m is also the maximum likelihood estimator of f of m. That's also another important property that we'll see in a moment. So the likelihood, I repeat Nauseam is still expresses the probability of observing the data you observe as a function of the parameter value. So, listen carefully. Given some data that you observe, the parameter values m low that make the likelihood small, okay, are disfavored. Why? Because it will be unlikely for nature to generate that set of observed data if the true value of m was m low. Clear? No. So if you have observed some data, you put them in your PDF. Okay? You put it in your P of x given n. Once you put the data, this thing becomes your likelihood. Okay? And which is a function of m. So you can evaluate this function of various values of m. Okay? You evaluate at a value, you pick a value, m low, and you have a very small value of this function. So your likelihood, once you...
When you mean small, I mean you mean you are far from the maximum.
Yeah, you're far from the maximum, okay? Then this value, m low, what does it mean? It means that if the nature had this value for the unknown parameter, the data that you observe would be very unlikely to be produced, okay? So this favors these values of m. Conversely, if you put a value m that put your likelihood to the maximum, this means that if the true value of m was this, your data will be very likely to be produced. So this favors values of the unknown parameter m around this. Okay? No, you're confused. Ask me a question, please.
Yeah, I have one question.
Yes.
So, doesn't this correspond to the Bayesian approach, but taking a uniform prior? So in the formula that we were given before, if you take a prior that is flat, don't you get that the posterior is exactly this?
No, this is, no, be careful. Don't, you know, the posterior and the likelihood are two different things.
Mm-hmm.
The likelihood, one-dimensional, multiplied by a flat prior, gives you a posterior that has the same maximum as the likelihood. But this is a particular case. But the likelihood is an ingredient that multiplied by the prior gives you the posterior. Now we're talking about the likelihood, and this likelihood is before the posterior, is something before the posterior, okay? So once you multiply by the prior, you get the posterior. But now we're talking just about likelihood, which is your model, basically.
Maybe what I'm asking is, would a Bayesian get exactly the same result by using a flat prior data frequentist, using the maximum likelihood?
In one dimension, yes.
But in more, not?
No. Not necessarily. And then it depends on the shape of the likelihood, but typically not necessarily. Do you understand what is the likelihood? No.
So you said in more dimensions, if a Bayesian uses a flat prior, they won't get the same answer as a frequentist. Is there a prior that a Bayesian can use in more than one dimension that would give them the same answer as a frequentist?
It depends on the problem.
But there are, for each problem, is there guaranteed to be one or not
I don't
necessarily?
know. I should work the mathematics, but I don't know how to do it.
Because then it seems like that's the right prior to use, right?
No, why not? Because Bayesian and frequentist answer to two different questions. So they answer to two different questions. So it's like asking when the train for Zaragoza starts and when the flight to New York starts. The fact that they start both at 5 p.m. does not mean that there is something particularly virtuous in that. They are two different questions. Sometimes they get the same answer, but it's, you know, it has no profound statistical meaning. Two different questions. Okay? So, remember, the value of m that maximizes the likelihood is not the most likely value of m, but it's the value of m that makes your data more likely. It looks like a game with words, but it's not. So,
well, because in that frequentist way of looking at things, you cannot assign a probability to m.
Exactly. So, this is an example that I invite you to work out. It's very simple. It's one of the few things that you can do actually analytically, and it's find the maximum likelihood of an exponential distribution. I don't have time to go through that now. And in the end of this example, this is for the lifetime of a particle, tau. In the end of this example, it shows that if your colleague, instead of measuring a lifetime, was measuring a width, a natural width, he would have the same estimate, which is an empirical proof that of the invariant property of the likelihood. The likelihood is invariant for reparameterization. Okay?
So if you do the same thing with Bayesian, assuming flat gamma or flat tau?
I'm not sure. In principle, they should differ because one of them is not linear, but I'm not sure. So, again, to fix very well the difference between PDF and likelihood. Suppose that you have a Poisson problem. Everyone knows the Poisson distribution, right? This is the model, P of j given mu, and as a function of j, this is the PDF, right? Function of the data. It's a discrete function of the data, because the successes you observe are discrete. As a function of mu is a continuous function of the physics parameter. Although the analytical form is the same, these are two different things. In one you put your data, 5 observations. In the other it's a function of the data, of j. Okay? This is a discrete function of j, this is a continuous function of mu. Same analytical expression though. Okay? Just to make sure that you don't never confuse likelihood and PDF. And this is illustrated here. So you have a Poisson distributed signal, no background, and observe 5 successes. You want to know the maximum likelihood estimator for the mean rate of success, right? Mu. So this is your observed value, this is the possible observed value, and you try. Let's try mu equals 0.5. Here the likelihood for this value is very small. So what does it mean? It means that if this was the true value, it would be very, very unlikely to observe 5. Okay? Now let's try 5. Oh, this is high. The likelihood for my observation is very high. So this is a good candidate maybe. And I try another one. 20. Again, very, very small in my region of observation, right? So I can write down the likelihood for mu at given 5. A given number of successes 5. This is a function of the data, this is a function of mu. These are continuous function, these are discrete functions. Okay? Well,
I have a question with the work of the estimator. So estimator is the parameter mu that maximizes the likelihood.
yes, you're right. I didn't look at the final. An estimator is a function of the data that estimates, which means measures some unknown parameter.
So in this case,
it's the maximum of the likelihood.
Okay.
Okay? Now we get the maximum of the likelihood. We know the best fit, but we don't know the uncertainty. How do we get the uncertainty in a maximum likelihood estimate? There are 3 ways. One is intractable, one is very long, and the other is approximate. Okay? The intractable one is do it analytically. You know, the analytical calculation of the variance of your estimator can be done if you have, if you know the analytical form of your model and know to do the integrals. I don't know, but you are theorists, maybe you know better than me. You can do it analytically. That's precise, rigorous, nice, and clean. Except Poisson and binomial and a couple of other examples, I've never seen it done. Okay? Then there is the other 2 options. One is to approximate the uncertainty with a theoretical lower limit that exists, and it's proved, and the other is to get it brute force from simulation. So let's go through these. The approximated way is to use the minimum variance bound. So the minimum variance bound, and I know this will remain a little bit up in the air, but I can give you reference if you're curious, is basically a theorem that states that the variance of an estimator is as high or higher than the inverse of the Fisher information. The Fisher information is a matrix here, which is connected to the likelihood and the parameters you wanna estimate, and basically is a measure of the information that is carried by an observation x over an unknown parameter n. Again, here is an expectation value, so it's an integral. This is the second derivative of the natural logarithm of the likelihood.
Sorry, that's an integral over what? Over x?
Over x, yes. Okay? So, of this slide, you have only to take, I know it's not going to make you happy because you want things demonstrated. You only have to take that there is some theorems that shows that that the variance of an estimator cannot be lower than something. There is a bottom, okay? So, and this bottom is reached by the maximum estimator when you go to infinite statistics. So when you have a real problem with finite statistics, you can still say, okay, I assume that I'm in infinite statistics and I take this bottom, this lower limit, as an estimate of my variance, okay? An estimate of my statistical uncertainty. And this is what exactly minuit does. Do you know what minuit is? Have you ever done a fit? Any theorists who do global fits here? All right, so you should do what minuit, or we do them with Mathematica. Okay, I don't know about the Mathematica minimizing, but minuit does this. Minuit approximates the variance using the minimum variance bound. Okay, it's an approximation. Many times is good, and it's basically the curvature of the likelihood at the minimum. The second derivative of the natural logarithm, so it's the curvature, okay? Of course, if you want to be sure that you're getting the right thing, the best way to go is to actually generate a lot of simulation. Generate a lot of simulation, choose a plausible value of the relevant parameter, feed into your likelihood, generate many data, and then fit, and look at the distribution of the results of your fit. That the spread of that distribution will give you the uncertainty. Okay? Not okay. Look at the plot, maybe it's clear. See, this is the result of the fit minus the true value that you put divided by the sigma of the fit. These are called fit pools. Have you ever seen fit pools in physics analysis? Really? So this is what I just said. In the end, if you want to know the distribution of your estimator, you simulate data, and you repeat your measurement on each of the generated samples. And the results, the maximum likelihood, will not be always...
Sorry, so x true there is what? What is x true there?
No, what confuses you is this should be mu.
And this is a plot of the likelihood?
No, this is a plot of the difference between the estimated value and the true value. How do you know the true value? You know because you generated, it's simulated. So you expect that your estimate is centered at true value, otherwise it's biased, and you expect, and the width of this thing will give you the uncertainty, right? The spread of your estimate.
Maybe you can explain it again. So in this, so how do you get all these data?
So each entry in this plot is the result of a fit on a simulated sample. Okay? You simulate a sample, you fit it, and you get a maximum likelihood value for your parameter, which should be m. She's right, I'm wrong. This is m fit minus m true. And then you get this maximum likelihood value, and you enter here. And you do it many times, and you enter many times, and you have a distribution. Okay? So, wait a second. So, if your estimate is right, this distribution should be centered around the true value that you generate in your tolerance. So if you do the fitted value minus the true value, you just move this distribution and you center at 0, okay? Now, when you do an estimate, you also need a statistical uncertainty associated with it, okay? So what is the statistical uncertainty? It's exactly the spread of your fit results over the various experiments. So it's this width here, that in this case is normalized by the actual statistical uncertainty of your fit, but it's basically the fact that it's spread out. You're lost.
Do you
So,
Go ahead.
do you put on one plot all of the, so you have to choose a range of plausible true ends?
You don't do, very good question. You do this plot for many possible values of n, because
Yeah.
you don't know the real value of n.
So you have many plots.
You have many plots in
Okay.
this. I don't have three-dimensional slide, but that would be okay.
so applying this to your previous case where you had these picking a j value, this is like then putting a spread, right? So in this value here, instead of having just the mu equals 5, you would have a spread saying mu is 5 plus or minus something.
Exactly. Indeed, this is one experiment. If you repeat this experiment many times, so you take mu, whatever is the true value, and you generate, sometimes you will observe j equal 5, sometimes you will observe j equal 6, sometimes 3, and then you have a distribution of the observed values as a function. Then you fit each, and then you get the distribution of maximum likelihood. Other questions?
Maybe I'm missing something here, but we have talked about, say, observing j equals 5, observing j equals 3. There is a step between the observation from your measurement and the underlying theory. And the underlying theory, in the sense that we don't observe some value of the physical parameter we observe. We need to interpret that with. Okay, sorry, I don't even know what I'm trying to say. It just seems. Sorry, are we calling j the
X is the data. Is X. It's what I call X.
Okay, right. So this is a statement about the observation of the data, not the observation of a physical parameter.
No. We never observe
because
physical
all of a sudden it felt like we were missing steps. If that was
No. Sorry if I confused you. No. J here. I need to uniformize the notation in my term. But J here is what I call X, and mu is what I call M.
Okay.
Is the fact that I steal material from other slide and then I'm lazy and I don't uniformize the notation. Go ahead.
How does this approach relate to sampling the likelihood when I want to do a parameter estimate?
Sampling?
Sampling the likelihood, because that's what people often do, right? Sample the likelihood and then give constant likelihood contours as your credibility intervals on the parameters.
The sampling of the likelihood sometimes done to get the uncertainty, right? If you have it depends. When you are in multiple dimension, sometimes it's hard to maximize your likelihood numerically, and so you do sampling, and you try to find where are the regions where the likelihood is higher, and then you also do contours to find the. But it's.
How does that relate to this approach here?
It's just. There is nothing conceptually different. It's just that when you have 36 dimension, the fit takes 1 week. You need to do 1,000 feet. You know that you already retired before having.
No, but I guess what she's asking is whether this distribution that you were getting is similar to the usual sampling, what you would get from the usual sampling.
No, because this distribution are the distribution of your maximum of the likelihood. This is maximum likelihood estimator.
This is repeating the experiment many times.
Yes. Sampling of the likelihood is that you have one experiment and you sample the likelihood to try to get a shape.
Yeah.
Okay? This is a technical problem. You have too many dimensions and finding a maximum in a multidimensional function is difficult. Okay? Go ahead.
The sigma in the x fit minus x true.
Yes.
Where does that come from?
This is,
Or is this something you put in afterwards
to add
to make
some
sure that
complex, since you're already very clear everything, this is this. This is the square root of this. This is the variance that the fit returns.
Okay.
And
then
the
you check
fact
it with
and the
this.
fact that this guy is width is 1 tells you that the approximation that the fit has used is actually good, because the spread is actually of that same.
That sigma of the fit to the Gaussian is 1.
Yes.
In M.
Yeah. So it means that the minimum variance bound approximation in this case is good. Very nice.
But if you didn't do that estimation, you could plot this without normalizing it, and then
You have the real answer.
Okay.
It's called residual. This is the pool in jargon, and the other is the residual. So what is the statistical uncertainty? Now we have seen how to calculate what it is, the statistical uncertainty you get from a maximum likelihood fit. this is the square root of the variance of the estimator, and basically it tells you that if you repeat the experiment many times, you would expect your result, your range of result, to include the true value with a certain probability. So if you take a statistical uncertainty 1 sigma, you would expect that if you take this is the fit result, so you got the central value and the statistical uncertainty, right? Look at it as a range, right? Forget about the central value, take from -1 sigma to 1 sigma, okay? So the statistical uncertainty determines the length of this range, okay? And the length of this range, if you have done things properly, is such that if you repeat the experiments many times, this range will include your true value with 68 or 95% probability. Okay? This is the meaning of statistical uncertainty. It's like what we see at the beginning with the error bars on the plot, you remember? So, it's important to realize that the true value is something that is fixed, in this case is m equal 2, and what is random is the range, is the result of your measurement, which in this figure are those intervals, okay? They fluctuate because each is taken from a different sample of data. But they fluctuate in a way in which 5% of them do not contain the true value, just this one out of 20, right? Because this is a 2 sigma, so it's 5%, 95% probability count. I see you lost. Please ask things. It's my fault if you're lost. Did you get this? It's important. It's the meaning of what a statistical uncertainty is. Okay? The statistical uncertainty defines an interval of your measurement results that contains the true value with a predetermined amount of probability. So you don't know if your very measurement, the results of your very measurement contains the true value. That you don't know, you cannot know. But what you know is that if you repeat your procedure on many other measurements, in average, 68% if your uncertainty is 1 sigma, or 95.5 if it's a 2 sigma, will include the true value with that probability.
So I have a question.
Yes.
So in this graph you've drawn, like, one of the lines doesn't have it contained within the 1 sigma.
Yeah.
But it's very close.
Now this is 2 sigma, sorry. Because
yeah, sorry.
Yeah.
Yes. Wait, so each of the individual lines is the lines once...
It's plus or minus 2 sigma. So
okay, plus or minus 2 sigma. So does it matter how close or far, if one of the lines was 5 sigma away or something like this, then is that going to affect your confidence?
No, because this is, again, this is an average thing. I mean, if you would repeat this thing and you see that every time this guy is here,
yeah.
I would think that the people who have done this measurement have made some mistake in the thing. But
okay, so the confidence interval doesn't care how far away the values that are far away are?
No, it just cares that that in average the desired fraction includes the true value. Okay? Go ahead.
I don't understand why we can't go from step 1 to step 2, because if I have these 20 experiments,
yes,
and I randomly pick one of those 20 experiments, then isn't the chance then still 68% that it covers the true value?
Yes, the chance is that it covers the true value, but I don't know if my own experiment does cover it or not, because I would have to repeat it 100 times.
But you can say that there's a 68% chance that your experiment has
the
true value.
That's true. Yeah, that's true. That's correct. So the language is important. The true value is not random. You cannot say I have 68% probability that my true value is within the interval. It's a kind of a picky point, but because frequentists are very picky about this, they like to think that true value is fixed and what fluctuates are actually the extremes of the interval, right? Because these are the function of the data. The true value is function of nature, whatever, God, whatever you would like to be. Okay?
I have a question.
Yes.
Related to, I mean, the first time we were talking about statistical uncertainty, it wasn't disclosed that there were many beams, and we said the data that we observed has not uncertainty, but we said this uncertainty, if we repeat
Yes.
the experiment in
Yes.
this beam, we will observe this fluctuation
Exactly.
with this 1 sigma range.
Yes.
But this is once we are taking, for example, in this case, all these beams and we compute the maximum likelihood and so on.
No,
for
no.
the
No. Those error bars were, if your experiment is how many counts I expect in this beam, that error bar there is this error bar here.
But with the same meaning, right? I mean.
Yeah, with the same true value for the expected number of events. In the
Okay.
beam.
Yes.
Okay. Same and unknown.
I mean, the center of the beam will always be the maximum likelihood, which will be basically the number of points or whatever.
Yes, because the Poisson peaks at the. So here this introduced the concept of coverage to the capability for an inference procedure, okay, to yield uncertainties that include, that cover the true value with a stated confidence level is the holy grail of frequency statistics, okay? So it's called coverage, and if your procedure does not have coverage, is not the proper frequency procedure. So coverage is a feature of the procedure. It's not a feature of your own particular result, like I said to you before. So the single interval resulting from a specific measurement may contain or not a true value. But what is important is that your procedure, repeated, produces intervals that contain the true value with the desired confidence level. Okay? It's just that, like in linear algebra, one define a vector as an element of a vector space with some properties. Here, you define a result as an element of a confidence interval set with some properties. Okay? And explicitly checking coverage against various choices of the true values is like for the Bayesian changing the prior. It's a very important cross-checking step in any frequentist analysis. Especially,
So what would you check?
well, to check this, you would generate many toys with various values of the true, various options for the true values, and then fit them and do your procedure on each. And then,
by simulation.
yes, by simulation. And then check that the results you get basically behave like this. So that the uncertainty you quote has 68% probability. Okay? This is very important, especially if you do global fits and then come out and say that lepton universality in Flavor is 5 sigma from the standard model. You need to check coverage because the statement is very, is very bold, and so you need to be supported.
So, I have one question. So at the end, we were showing there that we're imagining that the parameter is a constant that has some true value, but then we're measuring it through some other observable that at the end introduces this uncertainty,
Yes,
right? So now my question is, how would we differentiate if this actually is not the true constant of the theory? So what happens is that if actually this m that we are considering is not the fundamental constant, but there's something behind it, and this m has an inherent uncertainty as well.
That's a problem of the model. That means that your model, that you're trying to measure something with a wrong model. If the model that you take as a fixed m, but in nature m is the running coupling constant, and all these measurements have done at different energies, they won't have coverage. You will be confused very much, but it's not a problem of statistics. The problem is that the model is wrong. Like I said before, the model is very important, it's the most important piece. I need to finish. Yeah. Okay, I'm finishing
so we can
here.
Continue.
Yeah. Can you add a couple of hours of lecture?
Well, they are the tutors.
Yeah.
The tutor,
We will today.
So you can actually, because they are not overlapping, so you can go to all of the three and the same.
Okay. Thank you.
Okay, thank you very much.